Welcome to Independent Aircraft Investigations. My name is Richard Godfrey. Today we're going to investigate MH370 and the Ocean Infinity search technology. The Autonomous Underwater Vehicle, the AUV, is the workhorse of Ocean Infinity's search technology, and OI operates a large number of Hugin 6000 AUVs made by Kongsberg Maritime. AUV technology encompasses communication, navigation, sensing, automation, artificial intelligence, motion control, propulsion, imaging, detection, and machine learning. We're going to take a look under the covers of the AUV, how it works, what it can do, and how the AUV will find MH370. If you find this analysis useful and want to see future independent investigations, then subscribing to this channel helps ensure this work continues. Aviation news is covered on daily airline news as it happens. This channel is reserved exclusively for in-depth investigations. A Hugin 6000 is 6.2 meters long, that's 20.3 feet, and has a diameter of 87.5 centimeters, that's 34.5 inches. It weighs 1,850 kilos, that's 4,079 pounds. And its speed ranges from 2 knots to 6 knots, so 2.3 miles per hour to 6.9 miles per hour. It can stay underwater for up to 100 hours, depending on the mission and the payload. It has a variable payload with multiple sensors and instruments. One of the key items is the HISAS 1032. This is a high-resolution synthetic aperture sonar, a SAS system, used for detailed mapping and imaging of the sea floor. It is developed by Kongsberg Maritime in cooperation with the Norwegian Defence Research Establishment. And think of HISAS 1032 as an underwater camera, but made of sound instead of light. And it uses sound waves to create extremely detailed images of the seabed, even in deep or dark water where cameras cannot work. There's also a Kraken MinSAS 120, which is a miniature synthetic aperture sonar developed by Kraken Robotics with a 120 centimeter transducer array length. HISAS 1032 covers a much wider area per pass, up to 1,900 meters, total swath at 2.5 knots, and an altitude of around 100 to 120 meters above the seafloor. And that's designed for large area seabed mapping missions. The Kraken MinSAS 120 typically covers around 400 meters in total, but with a higher resolution, down to 2 centimeters post-processing imagery. The HISAS, by comparison, has 5 centimeter resolution. Overall, the Hugin 6000 has centimeter resolution, kilometer scale coverage, and precise bathymetry. SAS systems fly extremely precise lawnmower tracks, and even small course deviations can ruin a synthetic aperture image. Surveys usually overlap swaths by around 20% to avoid gaps. Synthetic aperture sonar records echoes from many successive pings as the vehicle moves forward. Then signal processing combines those returns as if they were captured by one extremely long sonar array. The remarkable thing is that the centimeter resolution can remain nearly constant across the entire swath. To combine hundreds of pings correctly, the system must know the vehicle position to millimeter precision. Even a few millimeters of position error can blur the synthetic aperture. SAS AUVs therefore rely on INS, inertial navigation systems, DVL, Doppler velocity logs, acoustic positioning, and precise motion compensation. An object 20 to 30 centimeters across can often still be detected hundreds of meters from the AUV. Each sonar ping records a waveform with a phase, the position in the acoustic wave cycle. At a frequency of 100 kilohertz, the wavelength is around 1.5 centimeters, which requires a position accuracy of around 1 millimeter. The longer the acoustic path, the more sensitive the system becomes to phase errors. This means very wide swaths push the limits of motion compensation. To maintain coherence, AUVs typically combine inertial navigation with Doppler velocity logs, pressure sensors, acoustic positioning, and micro-motion compensation algorithms. Advanced SAS systems also estimate motion directly from the sonar data itself, using what is called displaced phase center processing. This combination process is called sensor data fusion. In its most basic form, a navigation system can be implemented as a mathematical procedure known as dead reckoning, which estimates the current navigation state based on predictions of measurements of speed, direction of motion, and its previous state. Dead reckoning can be executed using kinematic models or dynamic models. A kinematic model is a mathematical model that describes how an object moves over time without considering the forces that cause the motion. It focuses only on position, velocity, acceleration, direction of motion, and how those quantities change. A dynamic model is a mathematical model that describes how an object moves and the forces or moments that cause that motion. It combines motion, position, velocity, acceleration, with forces and torques acting on the object. The 3D kinematic model forms the basis of the vehicle navigation system. The outputs include the 3D position, the 3D linear body velocity, and vehicle attitude in roll, pitch, and yaw. And in practical applications, there will be discrepancies between the true system and the modeling estimating it, leading to inevitable drift in model estimates over time. For underwater vehicles, two key error sources affecting dead reckoning-based navigation are the biases in the linear velocity in the body fixed frame, e.g. offset in the velocity model due to poor model calibration, and drift caused by the water currents. An inertial navigation system determines motion using internal sensors. Accelerometers measure linear acceleration, and gyroscopes measure angular rotation. From these measurements, the system computes velocity, orientation, and position through numerical integration. A Doppler velocity log, DVL, can provide both velocity over ground, known as bottom track when operating near the seabed, and velocity through the water, known as water track. When on the surface, the AUV can determine the position using GPS, Global Positioning System, but GPS does not penetrate seawater and therefore cannot be used underwater. A compass can still determine heading underwater because it measures the Earth's magnetic field. And several acoustic systems can provide underwater position fixes. LBL is long baseline navigation using seabed acoustic transponders. And USBL is ultra short baseline acoustic tracking from a surface vessel. And RAFOS is long range acoustic positioning. And TAN and SLAM are terrain aided or map based navigation. The Attitude and Heading Reference System, AHRS, provides stabilized orientation and heading information. And CDT sensors measure conductivity, temperature, and depth to characterize the water column and improve acoustic and navigation calculations. INS determines motion internally. DVL provides velocity relative to the seabed or water. GPS provides position when surfaced, and acoustic systems provide underwater position fixes. And compass and AHRS determine the vehicle attitude and heading, and CDT provides environmental measurements. And all of these measurements are combined using sensor fusion, and typically a Kalman filter-based estimator, to produce the vehicle's navigation solution. And this solution supplies the state information required for the guidance, navigation, and control system. Showing a picture of a Dornier aircraft wreck found in Oslo Fjord in Norway. The bright returns, the white areas, are hard reflective surfaces like fuselage sections and wings and engine structures. They reflect sound strongly back to the sonar. I'm showing a shipwreck. The sonar looks sideways, not straight down, and objects block the acoustic beam and produce shadows on the side away from the sonar. The length of the acoustic shadow depends on the object height, the sonar grazing angle, and the AUV altitude. From the image, we can estimate the wreck height is between 4 and 6 meters, and the shadow length is 15 to 25 meters. And typical SAS grazing angles are between 10 and 20 degrees. And that implies an AUV altitude roughly between 30 and 60 meters above the seabed, which is very typical for high SAS survey missions. Look at the bright sediment plume around the wreck, the orange area. This likely indicates sediment disturbance caused by currents interacting with the wreck structure. And over time, this creates a scour pit, which is very common around wrecks. This is what a Boeing 777 size aircraft would look like if you placed it on the seabed intact and then took high SAS imagery with an AUV at an altitude of 100 meters above the seafloor. From the around 60 pieces of wreckage from MH370 that have been found, we know that the aircraft will have broken up into a large number of pieces. The confirmed or highly likely floating debris from Malaysia Airlines Flight 370 strongly indicates that the aircraft fragmented extensively on impact with the ocean. If a Boeing 777 lies within a survey area mapped by high SAS class SAS, the engines would almost certainly produce bright, high contrast sonar targets with clear acoustic shadows, making them some of the most detectable pieces of wreckage. For Rolls-Royce Trent 800 engines, the fan diameter is 2.8 meters, 110 inches, and the engine length is 4.9 meters and weighs 6.1 tons. The AUV is electrically operated, and the battery pack is the source of power. AUVs typically use high-energy rechargeable battery packs, most commonly lithium-ion batteries, sometimes lithium polymer, or specialized subsea lithium packs. These batteries supply electrical power for the propulsion motor, which drives the propeller, the navigation electronics, the INS, the DVL, the compass, sonar systems, the SAS or multi-beam mapping, the onboard computers, mission control and data processing, as well as the communication systems, the acoustic modem or satellite when surfaced. Launch and recovery is over the stern. We're showing a picture of an AUV being launched. The ships in the Armada fleet carry several containerized AVU support modules on the deck. These containers function as mobile control and servicing stations for the AUVs. Inside the container, mission data can be downloaded, batteries replaced, and the AUV prepared for the next mission. The container modules support several operational tasks: mission planning and uploading the survey plan to the AUV, and when the AUV returns, the data download, retrieving sonar and navigation data, which was collected during the mission, battery servicing, removing depleted battery packs and installing fully charged ones, diagnostics, checking the health and status of navigation systems and sensors, payload configuration, adjusting sonar or other sensor settings before the next deployment. These containerized systems allow AUV operations to be carried out efficiently at sea, enabling rapid turnaround between missions. Instead of sending one vehicle to map the seabed, an Armada vessel can deploy several AUVs simultaneously. A typical workflow would be several AUVs are launched sequentially. Each vehicle follows a different survey track. All vehicles operate in parallel on the seabed, and after completing their missions, they return for recovery and servicing. Each AUV typically follows a systematic grid pattern, sometimes called a lawnmower pattern. Operating many AUVs simultaneously allows vessels like those in the Armada fleet to survey vast areas much faster than traditional single vehicle operations. Ocean Infinity is well equipped to find MH370 with superior data, navigation, and endurance. Number one, the SAS resolution does not degrade with range. Number two, large metal objects create very distinctive acoustic shadows. Number three, SAS systems can detect objects much smaller than their resolution. And taken together, that implies wide coverage. The system scans almost 2 kilometers per pass. High detectability, large metal wreckage produces strong returns, and shadow signatures, even partially buried wreckage remains visible. So if a Boeing 777 wreckage field lies within a high-SAS survey area, it is extremely unlikely to be missed. Currently, the vessels operate with a lean onboard crew, but the long-term goal is for these ships to operate without onboard personnel. Ocean Infinity's system allows vessels, AUVs, and other robotic systems to be controlled from shore-based control centers. Instead of placing a large crew offshore, the ship effectively functions as a robotic platform, while operators remain safely on land and supervise the mission remotely. Predicted tracks allow operators supervising robotic fleets to see the future behavior of each vehicle, which greatly improves situational awareness and coordination during large survey missions. That completes our overview of the search technology, in particular the AUV, the Hugin 6000. If you enjoyed this presentation, then please like us and please subscribe for future investigations. Thank you very much for watching and have a good day.